Select the major product of the following reaction. So if we look at what we have in this reaction, we see that we are starting with an epoxide. And we are reacting this with an alkyl lithium. So epoxides we know contain two electrophilic carbon atoms that can be attacked by a nucleophile. And if we look at our alkyl lithium, where we have a carbon lithium bond, lithium is more electropositive than the carbon. So you can say that has a delta positive charge, which means that the carbon that it's attached to is a delta negative. And this is actually a really, really strong base. I mean, we're calling this a partial negative, but we can actually think of this as being very, very close to ionic. So very, very close to having a full negative charge. So we can just say that it acts like it has a full negative charge. So this is a very strong nucleophile and a very strong base. And so what we will see with alkyl lithium reagents, because it's a strong nucleophile and a really strong base, we will see this react with acidic hydrogens. So reacts with acidic hydrogens. And it will also react with electrophiles. And so this both carbon atoms of the epoxide are electrophilic. And it is not a symmetrical epoxide. We notice that the carbons are differently substituted. So we have one carbon atom that we would call this a secondary carbon. So we're considering the bonds to other carbon atoms. We're not considering the bond to oxygen. We would consider that the same way we would like an alkyl halide, where we don't include the halogen when we're saying the substitution, because that bond between the carbon oxygen is essentially where you're going to have a bond break, and that's essentially what your leaving group is. And then, so we have that, we said that secondary carbon, so we're counting 2 bonds to carbon. If we look at the other carbon, we see only 1 bond to carbon, so that is a primary carbon atom. So with a really strong nucleophile, it will attack the least substituted carbon atom. So this strong nucleophile attacks the least substituted carbon atom of the epoxide. So what we need to do is we need to draw some arrows so we can see where the bond forms. So I'm going to redraw this structure. I'm going to use the abbreviation of phenyl to represent that benzene ring, just to save a little bit of space. So we see that, and we've got it attached on a wedge. And the wedge is really because of this carbon atom here that we've called secondary. That is tetrahedral, so it's got some 3-dimensional shape to it. And so there's our epoxide. And so I'm going to draw this alkyl lithium, and I'm going to go ahead and draw it as an anion, so that we can really see where the bond is being formed. So if that's an anion, that lithium is the counterion. So this is going to attack that less substituted carbon atom of the epoxide, which is going to break the bond between the oxygen and the carbons. This is acting as a leaving group, much like an alkyl halide would. And so we can look at what's formed. So we still have this wedged bond to the benzene ring. We know that that hasn't changed because we don't have any arrows involving that carbon center or any of the bonds to it. So that carbon is right here. We know that it still has a bond to oxygen because that bond has not broken. And that oxygen was neutral, but with this arrow, when we break it, we are putting an extra lone pair of electrons on the oxygen, which makes it negatively charged. And we just want to follow through the rest of our chain. So we see this carbon atom is still attached to the other CH2 from the epoxide. So we still have that bond to CH2. And that CH2 is now bound to the nucleophile. So this is what's happening here. You've got these lone pair of electrons coming in and opening that epoxide, but what we're really indicating is that we're forming a new bond between this carbon atom and this one. And so if we want to, we can number these carbon atoms just to keep track. So I'm going to start here on the epoxide. So we can say that's carbon 1, that's carbon 2, and so I can transfer these numbers into the product that I've started drawing. And so this bond carbon 2 is going to be bound to the nucleophilic carbon. So to keep the chain going in consecutive order, I will call that 3, and then go down the chain, 4 and 5. So I've added a 3 carbon atom chain. So there is that 3 carbon atom chain that I have added. And this would be the product of step 1. And then in a second step, we have water. And so what this is going to do is it's going to protonate the alkoxide so that we get a neutral alcohol. And so the alkoxide is the product from step 1. So it's still in its basic form because that's a very, very basic solution. And so in the second step, we are going to add water. And so the alkoxide, acting as a base, can take a proton from water, and we can break the hydrogen-oxygen bond. So we will often see this sort of aqueous workup. So sometimes you'll see water, sometimes you might see hydronium ion, H3O+. They're playing the same role. They're going to be there to neutralize if you formed a base in that first step, which we do with these organolithium reagents because they are strongly basic themselves. Okay, so let's draw the product. So it's going to look exactly like this, just the proton on that oxygen. And so then we have this carbon chain. And I'm going to go ahead and put the numbers back on there. So 1, 2, 3, 4, 5. And if we look at the options we have available, we should be able to identify that this is the structure shown here in D.